All right, let's go ahead and finish up our multiple choice section. So we have a certain spring, and once again, we're trying to find the work done in stretching the spring from its equilibrium length. So if you notice, I keep kind of emphasizing the same sort of problems. Let's integrate the force to get the work. So you can definitely expect a few multiple choice on these. So ax squared plus bx, sorry, negative ax plus bx squared dx. And we're going to go ahead and integrate this from 0 to d exactly as they indicate. So we're going to get negative ax squared over 2 plus bx cubed over 3 integrated from 0 to d. And so we end up getting choice C. Sorry, this is an older version where I had a typo there. So I will need to go ahead and make absolutely sure that I've corrected that before I hand this out to you. Then, number 17, we have a two-puck system, and we want to know the total energy of the two-puck system before they collide. So all we've got is kinetic energy. So this is actually kind of a weird question. 1/2 times 3/2 times 2 squared. I made the 1.53 halves just because it's easier. So I'm going to get 3 joules here plus the 1/2 times the 4 times the 1 squared. So that becomes 2. 3 plus 2. I'm getting 5 joules. Double check my math, but I got 5 joules. And then for number 18 and 19, so we are released from rest at a position R naught. So that means U of, so we have U of R naught equals U naught, and the kinetic energy is 0. And then at 2R naught, we want to know what the speed is. So we're going to have KE plus U at 2R naught. So energy is conserved. What that tells me is that I start off with a total energy equal to U naught plus 0, because my initial kinetic energy is 0. And that's going to become 1/2 mv squared here plus U at 2R naught, which happens to be equal to U naught. And you know what? A small little thing. So U at R naught is actually equal to 3 U naught. I need to go ahead and correct that. And at 2 R naught, the energy is equal to U naught. So what I'm going to end up getting is that 2 U naught equals 1/2 mv squared. So I'm getting 4 U naught over m equals v squared. And so what I'm going to end up getting here for my speed is choice C. And we want to know an expression for the force if we take the derivative. So let's do it. When we take that derivative, that's going to be negative 3/2 br to the negative 5/2. But remember, force is the negative derivative of the potential energy, so we need to put a positive sign here. And so I'm getting choice A. Then for number 20, we've got a car. Resistive force negative kV. Ooh, a little air resistance problem. And we want to know what's the speed and the position of the car after t equals 0. So let's be really clear. We're clearly running out of gas, so we do expect the car to slow down. So let's be clear on this. The other thing is that we're not moving at a constant speed. So here, just to be clear, we don't have any constant velocity, so that's clearly not right. And then the other thing here is that our position is, so A and E are clearly not correct choices. Let's just be clear on that. Because they indicate some kind of constant, some kind of like steadily decreasing velocity, I should say, constant acceleration. That's not going to work. What we need is we need a speed that's going to level off, and it needs to get slower and slower. So we need a speed that actually flattens out. That's going to eliminate choice C, because here what we're saying is we speed up. And that's not the right choice. So what does that mean? The other thing is that our position function needs to move forward with time. So that eliminates choice A again. That also eliminates choice B. And so what we're left with after all of our elimination is choice D. We need something that slows down going forward, and also comes to a rest. The other way to look at this is look at the functions and ask yourself which could be derivatives of each other. So, for example, this position function here, its derivative needs to be the velocity. So I need something that has a strong positive slope that gets closer and closer to 0, which is choice B, so that works. None of these others actually, I don't think they have correct derivatives, so that's definitely helpful. And that is it for our multiple choice problems. In the next videos, we will be doing free response.